He has been working for quite a number of years now, getting his PhD, which is about to finish, in the group of Adam Marshall and Seminario, which are the leading experts in Blazar research. And he's going to talk about Blazar in general today and his numerical modeling.
Great, thank you. Well, thank you so much for having me. It's a real honor and a pleasure to be here in Granada. And so the title of my talk is Blazars, Order and Disorder. And I've chosen for my title slide a painting by Goya, which I think is very fitting for a talk on Blazars. And the reason for this is that Goya, as an artist in the 19th century, was fascinated by depicting order and disorder in the world around him. And I think our own research at Boston University has really led us to the realization that the emission mechanisms in Blazars are profoundly ordered and disordered. So I think there's a kind of a nice union there. And I also like this painting of the Colossus because I think Blazars are truly celestial giants, and I hope by the end of this talk I will have convinced you of that fact. So just a brief outline of my talk. This is going to be basically an outline of my dissertation research, which focuses really around 4 different scientific questions that I'm trying to address. And so there are 4 sections in this talk, each surrounding a different question that I'm trying to answer. And so that's how I've basically organized my talk. And I'll end off just discussing some future work at the end of the talk. So to get right into this, the first question that I'm trying to answer in my research is how do orphan gamma ray flares occur within Blazars? And so by way of introduction to this topic, I'd like to start with the launch of the Fermi Gamma Ray Space Telescope in 2008, which has really ushered in a new era of high-energy astrophysics. And Fermi is a truly amazing instrument. It's a gamma ray space telescope, and it basically consists of a lattice of silicon detectors. And the idea is that a high-energy gamma ray comes into the array and pair produces into an electron and a positron. And the Fermi Space Telescope monitors the trajectory that these particles take through the array, measures its energies, and you're able to infer from where on the sky the high-energy gamma ray emanated. And after 8 years of continuous observation of the entire sky, Fermi has built up the following sort of gamma ray view of the cosmos. And so you can very clearly see the plane of the Milky Way, but all of these little point sources off of the plane of the Milky Way with circles around them are in fact Blazars. And what's even more fascinating about Blazars is that they exhibit variability on timescales ranging from months to days and even minutes. And so you can literally watch these galaxies flare up in high-energy gamma rays. And so the standard paradigm is what we're seeing is a supermassive rotating black hole that launches a relativistic jet along which blobs of plasma propagate. And if you have all that pointed more or less directly at you, you see what we call a blazar. Because that's the sun, by the way, in case you're wondering what that observation is there. But we can monitor these objects in the radio as well. So not just the high-energy emission, but the low-energy emission as well. And so my group is heavily involved with what is known as the Very Long Baseline Array, which is an array of 10 identical 10-meter radio antennas spread out across North America. And the idea is with the VLBA, you can perform very long baseline interferometry, preparing basically synthetic aperture synthesis, which allows you to observe as if you had a telescope the whole size of North America. And so it allows you to resolve these objects down to very, very small scales. And there's actually a wonderful synergy between Fermi and the VLBA because Fermi monitors the very high energy emission but with low resolution, whereas the VLBA monitors the very low energy but with high resolution, milliarc-second scales. And there's a wonderfully rich and variable structure that we see in the radio that emanates from these galaxies. So this is an animation showing you the variability over the span of a decade from one blazar known as Parkes 1510. So typically what we see in the radio is what is known as a bright radio core. It's a stationary feature at a given frequency. And then over the course of time, we see these blobs of plasma move away from the radio core at relativistic speeds. Now, in addition to monitoring the very high energy emission with Fermi and the low energy emission with the VLBA, our group in Boston has a dedicated ground-based campaign in the optical, including our own telescope in Arizona, which we use to perform optical polarization measurements. And in fact, there's a whole suite of observatories around the world that are involved in this campaign. And so with this wealth of multi-wavelength, high-cadence data, the following observational pictures come to light. So I'm showing you a series of light curves for this one blazar, Parkes 1510. So this is flux as a function of time. And in the upper panel, you're seeing the variability in the gamma rays, as seen by Fermi. In the lower panel, you're seeing the corresponding variability detected from the ground in Arizona. And this little arrow here demarcates one of these ejection events where we see a blob in the radio with the VLBA. And so typically what one sees are flares. Okay, and these flares, for the most part, tend to be highly correlated across the electromagnetic spectrum. So if you see a flare in the gamma rays, you tend to see a corresponding flare at lower wavelengths. There are, however, a subset of gamma ray flares that seem to occur in relative isolation with little or no variability detected at longer wavelengths. And these orphan gamma ray flares really challenge current models of blazar variability. All right, we have models that explain correlated variability based on shock acceleration in the jet, but to have an island gamma ray flare is very difficult. So that's the first question. How can these gamma ray flares occur in isolation? And we think the answer to this question is a sheath, the thing to put a sword in. And so if you were to think of a blazar jet as a samurai sword, then the blade would represent this relativistic spine along which these blobs of plasma propagate. And we think that this spine is enshrouded in a non-relativistic sheath of plasma. So what would a sheath buy us in terms of explaining these orphan gamma ray flares? Well, I got my start in the jet business running MHD calculations of these jets. Okay, so this is a simulation of a jet plowing into the ambient medium. It's a slice through a 3D calculation. Now the color scheme corresponds to density, with red being high and blue being low. So these jets are underdense. And as a result of that pressure mismatch, there is a strong recollimation shock that sets up at the base of the jet. So we got to thinking, well, what would happen if a portion of one of these non-relativistic sheaths were to be enhanced at one of these standing shocks? What that might buy you would be a very localized enhancement within the sheath plasma. In this case, a ring of shocked sheath. And the idea that we're going with here is that this ring, because it's immersed in the magnetic fields of the jet, will emit synchrotron radiation, creating a very localized source of seed photons that could potentially be inverse Compton scattered up to very high energies by the electrons contained within one of these blobs moving relativistically along the spine. Now I want to be clear that we envision this whole sort of radiative scenario occurring upstream of this radio core that we see in the VLBA. And the reason for that is that these orphan flares tend to occur shortly before we see an ejection event with the VLBA. So this is something upstream of the jet where we can actually probe. So to investigate whether this type of radiative scenario could actually drive an orphan flare, I wrote a radiative transfer code to basically model the non-thermal emission produced by one of these blobs as it flies through this ring of shocked sheath. So the results of that calculation are shown here. So this is an animation that I have on a loop. And what I'm showing you here is the variability in the spectral energy distribution of the light emanating from the blob as it propagates through the ring. So this is flux as a function of frequency. Now you'll see there are 3 curves here which correspond to the 3 different types of emission physics that I incorporate in my calculation, namely synchrotron radiation in blue, synchrotron self-Compton in green, and external Compton in red. So we're seeing the blob approach and then recede through the ring. And what you'll see is the red curve, the external Compton, varies quite heavily as the blob propagates through the ring. And this is because that emission is very sensitive to the angle that these photons coming off of the ring make with respect to the electrons in the blob. And it's that variability that can produce an orphan gamma ray flare. So to highlight that, I'm going to just plot up basically the 2 pass bands where we have data from those light curves. And based on the variability produced by this model, I can create synthetic light curves to then compare to the data. So that's shown here. So again, we're kind of zooming in on those 2 light curves I showed you earlier. So the data is in black, and now my synthetic light curves are in red. And so you can see the model does a fairly good job of capturing an isolated gamma ray flare with little variability produced in the optical. And so this is maybe potentially a plausible explanation for where these gamma ray flares come from. Now I want to stress that this model is by no means an explanation of all of the emission that we see from blazars. And to highlight that, I'm plotting up my synthetic SED with actual data. Okay, and you can see that I'm capturing the high energy emission, the gamma rays, but I'm not reproducing, for example, X-ray emission. That's not something that I'm incorporating into my code. So this is very much a niche market that I'm trying to explain. Now, an interesting result that came out of this study was the realization of how very sensitive the shape of these orphan gamma ray flares are to the nature of the acceleration of the blob through the ring. Now, to demonstrate that, I've kind of carried out a little mini parameter survey where I basically tweaked the nature of that acceleration to see that I get different shapes of orphan gamma ray flares, depending on whether I accelerate or decelerate. And I think that's exciting because it highlights the potential of using these orphan gamma ray flares to intuit something about the nature of the acceleration of these blobs upstream of where we can actually probe with the VLBA. And then one final kind of tangential aspect of this research is that there's a group studying neutrinos in Antarctica that they think are occurring or being produced by pair production off of spine and sheaths within blazar jets. And so it's kind of an interesting aside, but that there's potentially a lot of science that's coming out of this kind of structure within a blazar jet. So that's the end of my first section, which brings me to the next question, which is, can we actually go out and observe a jet sheath within a blazar? Because up until this point, it's been all very theoretical and hand-wavy. Maybe there's rings and sheaths and spines. It would be actually nice to have some sort of observational benchmark that these regions of plasma are actually present within a jet of a blazar. So what would that look like? So I'd like to show the following cartoon, which is basically just a schematic of what we think the magnetic fields within a jet are doing as we move out from the central supermassive black hole. And the idea is that very close to the central engine, the magnetic field should be predominantly toroidal or helical in nature, owing to this rapid rotation. Now, as you move further along the jet, these fields, it's conjectured that these fields can become increasingly poloidal or stretched out in nature. And so the big question is what is the topology of the magnetic fields on the scales where we can probe with the VLBA? And so one scenario for what that might be would be a spine sheath structure. And the idea is that shear between the jet and the ambient medium would take this initially toroidal or helical magnetic field and stretch it out to be aligned predominantly parallel to the jet axis. Now, a prediction of this is that if you were to take a transverse slice across the jet, you would expect the fractional polarization to increase towards the edges of the jet, with the orientation of that polarization being indicative of magnetic field that is parallel to the jet axis. Now, the problem with this is that this signature, this polometric smoking gun, if you will, of a smoke sheath, is going to be a very faint signal. And the reason for this is you've got basically this non-relativistic sheath sandwiched right next to this relativistic Doppler boost spine that is pointed directly at you. So it's going to be a very faint signal to pick up. Now, in an effort to try and see this, what we've done is to implement a method of radio map stacking. And the idea here was to go back through our observational campaign, which has been running for almost 7-8 years now, and to basically cherry pick epochs of quiescent jet activity and stack them together based on the location of this radio core, which we pray is stationary at a given frequency. All right? And the idea by doing this is that all of this transient phenomena associated with these blobs moving along the spine will cancel out in the stack map, and any static underlying structures like a sheath will be built up. All right? So the results of this stacking procedure for this one blazar that I've been talking about, Parks 1510, are shown here. So this is a stacked map of 20 different observations over 7 years combined together. Now the black contours correspond to synchrotron emission, with the underlying color scheme highlighting the polarized component of that emission. Now these black line segments that I've plotted up here are called electric vector position angles, or EVPAs. And they give you the orientation of that polarization as projected onto the plane of the sky. Now, a very important point is that barring effects of relativistic aberration or Faraday rotation, these EVPAs, these line segments, should be predominantly perpendicular to the projection of the magnetic field onto the plane of the sky. Now, to guide your eye, I'm going to plot in red here a nominal jet spine based on the historical trajectories taken by these blobs of plasma. And what you can see is that these EVPAs are predominantly perpendicular, if not inclined, to this jet spine. And that's the signature of jet shear. It's demarcating a region of magnetic field where the magnetic field is parallel to this jet spine. Now, to be a bit more quantitative, I've taken a series of slices through this stacked map to get a feeling for how the various Stokes parameters vary transverse to the jet axis. And so I'll show you these profiles for this first slice. So in the upper panel, you can see the profile along the jet axis, or rather perpendicular to the jet axis, of the total intensity. Okay, that's the Stokes I. In the second panel, I'm showing you the polarization profile. That's the combination of the Stokes Q and U. And most importantly, the third profile here is the fractional polarization, which is the ratio of the first two. And as predicted by the spine sheath scenario, you can see that that fractional polarization increases towards the edges of the jet. So it's this signal in combination with the orientation of these EVPAs that is indeed the polometric signature of a jet sheath within Parkes 1510. So that's exciting. That's what we were after. Now, to get a better feel of the extent of this sheath within this blazar, along each of these slices, we've aligned our total intensity profile with the polarized profile and used the double peaks in the polarization to guide us to the nominal location of the sheath along each slice. And then I repeated that for all of these slices, tracing out this shaded gray region, okay, which is our best guess as to where the sheath is in Parkes 1510. And with that in place, I then simply add up the light that I see in that region, and I come up with an estimate, a crude estimate, but an estimate nonetheless, of the bolometric luminosity of this sheath, which is around 10 to the 45 ergs per second, which is a not negligible amount of seed photons, and is in fact enough seed photons for my ring of fire model to drive these orphan flares. And so we think, at least in the case of this one blazar, Parkes 1510, the whole thing might hang together as a viable explanation of these orphan gamma ray flares. So that's the end of the second section of my talk, which brings me to the next question, which is, we've done this case study for this one blazar, Parkes 1510, but how common are these orphan flares? How common are sheaths of plasma in blazars? We know that these orphan gamma ray flares are not exactly in the majority in terms of the types of flares that we see, so it'd be nice to have some sense of how common these objects really are. Is this phenomena reoccurring, or is it really just a case-by-case basis? So to answer this question, I went through all of our archival data over 7 years looking for other examples of orphan gamma ray flares. And when I found one, I basically went into the radio maps and performed this stacking to see if I could find another signature of a jet sheath. And so I did indeed find other examples. This is a stacked map for another famous blazar known as 3C273. And 3C273 is a great blazar because it's so close to us. So close, in fact, that you can actually see the jet in the optical with HST. So it's a very famous blazar. And in the stacked map, there are sort of actually two very distinct polarization features that jump out at me. First off, there is a structure at the very base of the jet where the EVPAs are, in contrast to before, aligned parallel to the jet spine. Whereas downstream, we see more regions where we have EVPAs perpendicular to that jet spine. And so the physical interpretation of what we're seeing here is a strong shock, okay, at the base of the jet, which is taking a disordered field, compressing it, and orienting it perpendicular to the jet axis. And so again, this is why I've chosen this theme of order and disorder. We see this within blazar jets. Now downstream, we see more regions of examples of this jet shear. Okay, so playing the same game of slicing and dicing, you can see how distinct the polarization features are in this shock region in contrast to downstream, where we see this bifurcation again in the polarization, which is this jet shear signal. And sure enough, we find an example in our multi-wavelength light curves of another orphan flare that was associated potentially with an ejection event with the VLBA. And this ring of fire model is able to do a fairly good job of capturing this orphan flaring behavior. Here's another example. This is 3C279, very bright blazar. And again, the same process of stacking and slicing. We see this fractional polarization, this polometric signature, and there's also an example of an orphan gamma ray flare. This is a very interesting flare, though. I want to point out there are sort of three really pesky data points that I tried very hard to make go away, but they are statistically significant. And so I leave them up there, and maybe something catastrophic is happening in the electron population within the blob. I'm unable to put a kink in my orphan flares. So that's something I'm still very much thinking about. But that's another potential example of one of these orphan flares. This is a Blazar 4C7107. We actually had a press release about this Blazar. This is a stacked map, the same signature, and we actually think we're seeing maybe potentially a pair of orphan gamma ray flares go off here. Although very admittedly, the optical coverage, I've only got one data point, so maybe there's an optical flare in there, but I'm going to sell it as an orphan flare. But you know, we're very mindful of the sparse coverage we have for this particular Blazar. And then finally, this is a Blazar CTA 102. I was actually alerted to this particular Blazar by the group here at the IAA. This map is still very much under construction, but I'm starting to see that hint, at least on one side of the jet, potentially a shear layer. And there was an orphan flare that went off, sort of flanked by two ejection events with the VLBA. And so we had to go at modeling that as well. So I think potentially this concept of the radiative interplay between a jet spine and a jet sheath is perhaps a viable explanation for these orphan gamma ray flares. So this brings me to the final section of my talk, which is still very much in the arc of polarization studies within blazars, but is actually a very distinct question, which is, can circular polarization be produced within a turbulent jet? So up until now, I've been talking to you about linearly polarized emission, but there's a very distinct form of polarization, which is circularly polarized emission, the Stokes V. And this is potentially a very powerful probe of the plasma within the jets, which after many decades of blazar research, we still don't have a firm handle on. And so circular polarization might be the key to unlocking what these jets are actually made of. Is it electrons and positrons, electrons and protons? We really don't know. Now, to introduce circular polarization, I need to talk about the concept of birefringence. All right, so this is a picture of a terrestrial example of a birefringent material, a quartz crystal. And the idea is that imperfections in the lattice of the crystal produce an optically anisotropic environment. So as light propagates through the crystal, it experiences varying indices of refraction, which results in this complicated web of lines produced from this uniform grid of blue lines behind. Now the idea is that in blazars, in an astrophysical context, if the jets are turbulent, you could get different cells of plasma within the blazar that have different orientations of magnetic field. And that will produce an optically anisotropic environment, a birefringent environment, whereby linearly polarized emission produced by synchrotron radiation in one part of the jet could be converted into circular polarization, which would perhaps unlock the key as to what these jets are made of. And this has actually been seen in a few blazars, most notably 3C279. And so on the right, I'm showing you contours. This is from Hamann et al. I'm showing basically contours of synchrotron emission. In the middle panel, you're seeing the polarized emission, the linearly polarized radiation, again with the EVPAs giving you the orientation. But on the right is a plot basically of contours of circularly polarized emission, the Stokes V. Now this is a very faint detection. It's typically only 1% the total intensity, but again is a very powerful probe. So my supervisor in Boston has developed a new model of blazar emission based on these recollimation shocks that I showed you earlier in the MHD simulations. And the idea is that he simulates this radio core region, this static feature that we see with the VLBA, as a standing recollimation shock and rarefaction fan, across which thousands of turbulent cells of plasma, each with distinct magnetic field orientations, propagate. And the idea is that the aggregate of all of these cells of plasma can potentially produce a birefringent environment within which circular polarization can be produced. And so the question I'm trying to answer is whether this model can reproduce the circular polarization at these sort of percent levels that we've seen with the VLBA. Which brings me to solving the full Stokes equations of radiative transfer. And this is my one big equation for the talk, so I hope I won't put you to sleep. But this is them. This is the total equations that govern the transfer of polarized radiation through a source. So on the right, I have what I want, the four Stokes parameters, the I, the Q, the U, and the V. On the far right, I had basically a series of Rybickian-Lightman style emission and then corresponding absorption coefficients for each of these Stokes parameters. There are two coefficients pertaining to the effect of Faraday rotation, whereby linearly polarized radiation can propagate through one of these cells of plasma and be attenuated and have the essence of the orientation of that polarization rotated. Okay, so that can affect what we see, all right? And that needs to be taken into account because each of these cells in this model are potentially a Faraday screen for radiation from adjacent cells. So you need to be mindful of that. There are also two coefficients pertaining to this birefringent effect of Faraday rotation, whereby you convert that linear polarized emission into circularly polarized emission. And then finally, there's a series of convective derivatives that just wrap into optical depth effects, the attenuation of the radiation as it propagates through the medium. And so this big ugly equation has a nice analytic solution whereby what comes out of a cell is equal to what went into the cell, combined with what's intrinsic to the cell, plus a whole lot of math pertaining to these Faraday effects, which is what I'm interested in. So the idea is to take all of that and then cast rays through the computational grid and then make synthetic images to see what is the levels of polarization that we would get out of a model like this. So I've taken all this formalism and I've embedded it into a ray trace code called RadMC3D, which was written by Keys-Dolman at the Max Planck in Heidelberg. It's a wonderful code, and it's written in a very modularized fashion. It was originally designed for dust radiative transfer in protoplanetary disk simulations. But I basically just took out all the dust physics and I put in all the synchrotron physics. And it comes with a very nice Python wrapper for visualizations. So I'm going to cut right to the chase. This is a three-dimensional rendering of the magnetic fields within this TENS model. And again, the theme of this talk is order and disorder. So there's actually a dial in the code that allows you to tune up or tune down the level of disorder or order within the simulation. And so for my first ray trace, I started with a very ordered magnetic field grid. And so each of these vectors is showing you the orientation of the magnetic field within an individual cell of plasma within the model, color-coded by the strength of that field in Gauss. So the output for the TENS code is the input for my ray tracing program. And so what my ray tracing program produces are maps of these four Stokes parameters, the I, the Q, the U, and the V. So if I combine, for example, the Q and the U, I can create a synthetic polarized emission map. So this is comparable, again, the color scheme corresponding to the polarized intensity with the black line segments showing you the orientation of the EVPAs. Now we're looking basically down the barrel of the jet. For this particular ray trace, I've chosen an angle of inclination of 6 degrees. Okay, we're looking at 43 gigahertz like all the images I've showed you before. Now to get a better sense of, we're seeing this all in projection, but to get a better sense of the model, I like to toggle from the co-moving frame where the plasma is at rest, which is where we do all the radiative transfer, so that you can kind of see the structure of the TENS model. And if I switch to total intensity, the Stokes eye, you can see that it really is just a series of concentric cylinders within which we have all these turbulent cells of plasma embedded. Now, most importantly, going back to the observed frame, here is a plot of the fractional circular polarization. This is V over I. And what you can see here is that climbs up to around 3%, which is actually pretty high, but it's not 10% and it's not 0%. So this is sort of encouraging that this model might actually work. Now again, toggling back to the co-moving frame, you can kind of see this wonderfully kind of symmetric structure where we go from positive to negative circular polarization along the length of the jet. And that's interesting. I'm sort of beginning to think about what that's telling us about the plasma. Now, as I said, this talk is about order and disorder. So coming back to the TENS model, this is another ray trace where now I turn up the disorder because we think these jets are turbulent. So instead, we have a very chaotic magnetic field structure contained within this recollimation shot. So the results of the ray trace for this simulation are shown here. So again, we're looking at polarized intensity, which is still quite high. And the reason for that is that you can see that basically the TENS model takes an initially tangled or chaotic or disordered magnetic field, compresses it, and you get order downstream of the shock. And so we're sort of looking through that. And here's a plot, again, of the fractional circular polarization. And I guess the exciting thing here, it's not much to look at, and the thing that I'm most excited about is the fraction, that it gets up to around 2%, which is actually pretty comparable to what we've seen in the several blazars where we've detected the Stokes V. So I think the results are encouraging. And I think going back to the original question, can a turbulent jet model produce circular polarization? I think the answer is yes. Now, in terms of future work, I'm plotting everything in terms of Janskys per pixel. So it's as if we have a very powerful interferometer. But what I need to do is take a map like this and then convolve it with a point spread function indicative of the resolution that we can actually obtain with the VLBA. And so I need to sort of vet these results through this procedure. I haven't done that yet, but that's future work. So that's the final section of my talk. For the last 10 minutes, if it's all right, I'd like to kind of end off by just sort of outlining where I hope my research will go in terms of future work. And this actually kind of, in terms of future work, I'd like to kind of return to my past, which is these MHD simulations, which is where I started in Canada in terms of my research with jets. And to get a kind of more holistic view of this phenomenon, I'd like to start off by showing a picture of a radio galaxy, which is ostensibly a blazar as seen at right angles. Okay, the idea is that these are all one phenomena, and it's just line of sight effects that are the difference between whether you see a blazar or a radio galaxy. And these objects are truly immense. These jets extend out to kiloparsec scales. So what we're seeing here is a bright radio galaxy, and then these huge jets that end in these radio hotspots, which we think are shocks where the jet finally impacts on the extragalactic medium. And these are kiloparsec scale jets. And so these objects, in contrast to blazars, are best studied with the VLA or the JVLA, which is very sensitive to larger scale, lower intensity emission in the radio. And so what you see in terms of multi-wavelength observations is a very distinct structure depending on what frequency or wavelength you look at. So for example, this is an old observation, but an awesome observation nonetheless of Cygnus A at 2 centimeters. So you see this bright radio core and these hotspots. If you go to longer wavelengths, say at 20 centimeters or 92 centimeters in this case, you see this extended structure which we call a radio lobe. And the idea here is that what we're seeing is the effects of synchrotron cooling. The idea is that these electrons are out there immersed in the magnetic fields of the jet. And as they emit synchrotron radiation, they lose energy, they cool. And so depending on which frequency or wavelength you use, you probe different radiative histories within the jet. Now again, I started from a magnetohydrodynamics point of view, solving these simulations where we follow these macroscopic scale flows. And the idea was, how do we capture basically the radiative essence of these jets? And it's a major problem to this day in MHD simulations of jets. And the reason for this is that the scales between the microphysics of the electrons and the macrophysics of the jets are so huge that numerically it's next to impossible to combine all of those in a self-consistent fashion. And so one thing that jumped out at us in doing these MHD simulations was how distinct the shock structures are within the jet. We see this recollimation shock that I was talking about earlier. In addition, there's a termination shock, which is this region where the hot spot is, where you're impacting the ambient medium, and then a surrounding bow shock. And so we think that these regions of shocks accelerate the electrons. So you have electrons come in the jet, slowly cool, but they can get re-energized through the Fermi mechanism at these shock structures. And so to kind of model the microphysics of that shock reacceleration in an MHD code, I came up with a numerical algorithm whereby you could just introduce one new MHD variable, the synchrotron age, the radiative history of the plasma, and you can track that in your simulation to sort of emulate these synchrotron losses. Now, to account for basically this shock reacceleration, we realized that we could reset this synchrotron age based on the ratios of the pre to post-shock density, internal energy, and magnetic field, which are these global MHD variables, all of which could be tied back to the velocity divergence, which tracks the strength of these shocks. And so this is a very efficient way, without doing all the microphysics, to track these radiative histories. And it's a very simple algorithm, very inefficient, or rather efficient way to incorporate this type of physics into an MHD calculation. And so this is showing you the effects of this synchrotron age variable. So in the lower panel, I'm showing you the shock. Okay, that's the velocity divergence. In the upper panel, I'm showing you the synchrotron age. So blue is young and red is old. And in the middle panel, I'm showing you the effect of this shock term. So you can see at the location of this shock, that age gets rejuvenated. Okay, you get a young population of electrons present. And so the idea here is you really want to have something in the Lagrangian frame. These codes are Eulerian by design, so they have the flow pass through a grid of cells. But you want to have something moving along with the jet. And so we introduced a series of what I call quarks. They're essentially sensors that bob along with the flow, recording the MHD variables they experience on their trip down the jet. And so you can pick one of these sensors in the shock region, and what you can get is a history of its experience moving down the jet. And so you can see for this particular quark, it experienced 4 very strong shocks on its passage down the jet, which results in the resetting of this synchrotron age variable proportional to this new term. And so the result of this is it allows you to do ray tracing through an MHD calculation now, but at multi-wavelength observations. And so at 20 centimeters, you see this extended synchrotron emission from the old aged electron populations. But if you move to shorter wavelengths, say at 2 centimeters, you're seeing more energetic flow along the base of the jet. And so in terms of future work, what I would like to do is to move from MHD simulations of kiloparsec scale jets to RMHD calculations of parsec scale jets, and to combine an algorithm like this with polarized radiative transfer so we can really start to compare numerical simulations to the observations that we have with the VLBA and the VLA and really make one-to-one comparisons. But I think I've talked long enough, so I'm going to end it there and open up to questions. So thank you very much. I hope some of that made sense.
That was a great answer. I have a question regarding the production of circular procession in the model. You showed 2 cases in the simulations that you made. One of them was using some kind of level of turbulence, and then you showed levels of circular precision up to 2%.
Yeah.
Localized frictions. You have actually some changes between
between the front of the jet and the back of the jet.
But then in the well-ordered case, you also had circular precision production up to 3%.
It was higher.
So, I mean, I understood that you were simulating production of circular precision because of
conversion
fringes in different structure of the magnetic field and different cells of the model. So what was the mechanism for producing the circular precision in the ordered?
In the ordered version. So I've been worried about that since I first saw that plot. And I had a conversation with several people that do this. And I guess the idea there is that the circular polarization is a distinction between the magnetic field in the spine of the TEMS model and the surrounding outer layers. And I think the idea is that you're getting some sort of orientation effect whereby you're getting the back propagating through the front. And I'm not sure why that produces circular polarization at higher levels. Because my intuition was that the turbulent case should have higher levels because you've got more different sort of orientation effects along a given line of sight. And so that's something that I'm very much going to look into, and I actually don't have a firm answer for you. So I'm worrying about it as well. So that's something to look into.
It may be possible that what you have for the non-turbulent case is that the circular polarization is actually intrinsic from your synchrotron.
I'm not sure that I'm not sure that I've actually, unless that's in the formalism that I showed you in that big equation, in all those kappas and alphas. My understanding was the intrinsic was not there, and so I'm not sure that I've actually incorporated that. Something I need to investigate as well as to what, because there are actually several different mechanisms by which circular polarization is produced. But I was under the impression that what I had coded up was the Faraday conversion, and so I need to double check whether, in fact, there is intrinsic there. But my intuition is still that in the turbulent case, that should be higher than in the non-turbulent, and so that is a troubling result for sure.
It looks like you may have some cancellation also.
In
turbulence, which may produce a smaller circular polarization that you have.
In terms of depolarization, you mean? Yeah. So that'd be neat to, I've only shown you observations at one specific frequency, and now the thing to do is to turn the frequency dial, and you could make maps of yeah, exactly. Yeah.
I have a question also. According to your talk, then the orphan gamma ray flares are associated with the external content coming from the particles in the ring.
Yeah.
does it mean that there should be always another flare
This
that
is
should be associated
yeah,
to it?
this is a
that
great
correct?
this is a great question, and the answer is no. Well, it's a fascinating thing that I looked in because you'd think naively that each jet should have a sheath of plasma. So why don't we see orphan gamma ray flares all the time? And we don't. And so there's an example. I didn't show the stack map of 3C454.3, which is the brightest gamma ray source in the sky. There's not a single example in 7 years of data of an orphan gamma ray flare. And I went through, just because it's 3C454.3, of stacking these maps looking for a sheath, and I saw no example of these EVPAs perpendicular to the axis. So maybe somehow the sheath only gets enhanced for a short period of time, and then that ring fades away. So another thing that's I'm very interested in is in these maps of 3C273, where I see the sheath downstream. It would be amazing if we could track one of these blobs as it propagates through one of these regions to see if we could predict an orphan flare before it happens. But I haven't done that yet. So it's a very good question. I worry about it, but I don't have an answer for it. Yeah.
Thank you for the book. So your last question, how you define exactly the turbulent jet?
Yeah, it's a. This is again. I wish my supervisor were here. This is sort of the innards of his code. But the idea is that it's a power spectrum of fluctuations that sort of follows a Kolmogorov type spectrum, where you cascade from large scale to small scale turbulence. And so what his code is doing is basically feeding in one of these power spectrums motivated by observations, where we see this flickering, this turbulent scale, fluctuations in the polarization, and he feeds that through the cells. And then all the cells orient themselves based on this turbulent spectrum, and then I take a snapshot through. But you raise a very interesting point, because this code, this TENS model, is statistical in nature. So it can't really produce an individual snapshot. Every time I run the simulation, it's different. So I'm sort of just looking for what is the overarching sort of topology or levels of polarization that we see. But it's really turbulent in nature. So that's the idea. I don't know if that answers your question, but that's yeah.
But it's mainly when you are using the radio data, no?
Yes. His original motivation for designing this was, we see in the polarization these swings in the EVPAs, the orientation of that polarization. And in contrast to these stacked maps, where you see this nice large-scale structure and gradient, on small time scales, it's just flopping around, which sort of speaks to a turbulent nature in the jet. And so that's what his original motivation was, to try and simulate that.
I may have another comment. Have you computed the time variability for the case of the TNSD model to check what it would be the expected variation, polarization and circular polarization?
As a function of time, that's on my to-do list when I get back. So I've only taken a snapshot of the first, t equals 0, just as a proof of concept that the polarization is there. The step now is to follow these things through different snapshots to see how that changes, and that's very much on my to-do list. Yeah.
Another question. So I'm not sure if I missed how many sources you have exactly in your sample, but in how many of them you are able to see these signs of turbulent jets, and then to get information about
Yeah.
circular
I think in contrast to the orphan gamma ray flares, which are just a handful, the turbulence is a more ubiquitous signature. And so I think almost all of them show EVPAs that flip around, although there's of course a gradient from source to source. But I think it's, I think there are a total of 35 sources that we're monitoring on a monthly basis. And I'm pretty sure the majority of those show a chaotic behavior from at least time to time. Although sometimes it switches. This is a really frustrating and beautiful thing about Blazar research, is you pretty much see everything you could possibly imagine. And so we see situations where it's very chaotic, and then suddenly it'll go very smooth, and you get structured variability in the polarization. And these are all open questions still. So, yeah.
Last question. Mine.
Yeah.
So just in optical, you said you are doing the monitoring of your samples. So what is the frequency that you are?
I'm pretty sure it's primarily the data that I've been working with is in R band. I don't work so much with the optical data. I just get handed these light curves, but I know there are.
You observed it.
Say again?
How often?
I think it's a monthly, I think Svetlana goes every month. It's a monthly cadence to sort of mirror the cadence that we have at the VLBA. Of course, ideally, there's studies, some fascinating studies in our group on microvariability. There's one postdoc who's working with Kepler data where you're literally monitoring the variability on timescales of minutes. You know, it's fascinating, and there's variability, so it's there's a lot of work to be done for sure.
Okay, thank you very much.
Thank you very much.